Right, there's the first slide. So, as you can see, I'm going to be talking about multi-component droplet evaporation in the context of GDI spray modelling for CFD models, and including looking at superheated droplets for flash evaporation. Okay. Quick overview. First, some motivation for why we're looking again at multi-component droplet models. I'll introduce the theory briefly for evaporation of a droplet, and then I'll look at our contribution to the existing work out there on droplet evaporation, in particular looking at droplet superheat models, or model for flashing gasoline sprays, and also the influence of non-ideal mixture for gasoline. That's really due to the ethanol content in the gasoline. I'll present some results for both a binary and a multi-component gasoline model with 8 components in, and then we'll finish with the conclusions. Okay, so on the right you can see a spray CFD picture from an open foam simulation of just one plume of a multi-hole gasoline injector, and we can see lots of parcels of droplets in there, and each of those parcels is tracked in a Lagrangian particle tracking sense, much like the bubbles in the previous presentation, and the fluid, or the vapor phase, is Eulerian. For spray modelling, as you probably know, there's a lot of sub-models required that deals with how the droplets interact with their environment, and that's not a comprehensive list, and we're going to be focusing on the evaporation model here, and the sort of reason for looking at that again in detail is, as we've seen at various points today, we really want to get that prediction of fuel spray vaporization correct, because we want to know where the fuel vapor is in the cylinder. We want to make sure it's not. We want to make sure the droplets are not hitting the wall or the piston before they've actually evaporated, and amongst other things, that helps keep our PN emission down. Okay, so I'll introduce. Well, okay, that's supposed to come up one at a time. Okay. So the key point of the model that we started from is that we model the droplet temperature implicitly using the heat equation for the droplet. So we track a full description of the temperature throughout the droplet throughout its lifetime. We have fully temperature, pressure and composition dependent vapor phase properties based on some reference condition. The droplets tend to move very fast relative to the air that they're moving through, so we need to account for the fact that there's going to be internal motion inside the droplets due to shear on them from the air. That will enhance heat and mass transfer inside the droplets in the liquid phase. This is the equation for, well, this bit's the equation for evaporation rate from a droplet, and it's based on this Spalding mass transfer number. And you can almost see the fact that the reason we're spending so much time and effort modelling both the evaporation and the temperature of the droplets is that they're coupled quite strongly through this boundary condition that's half there, which is, as you can kind of see, boundary condition for liquid temperature is proportional to evaporation rate. So it's all linked up. So that's all in the literature. Okay. So our first contribution is in droplet superheat modelling. We've taken a slightly different approach to what is seen in the literature. We use a slightly different expression for evaporation rate, which is based basically on energy being the limiting factor. We can't quite assume that a superheated droplet is going to evaporate instantaneously. we know that doesn't happen, even though the previous expression would predict it does. So the energy is the rate determining step here, which comes from typically inside the droplet if it's particularly hot. So our approach has been, initially we limit the droplet surface temperature to the prevailing boiling temperature of the current mixture. Then we just solve the equation as before, so no extra models needed. And we just adjust the boundary conditions to make sure the droplet doesn't try to boil away during its lifetime. The enhancement to evaporation comes through this reduced effective latent heat of vaporization due to the negative gradient of temperature from the hot inside of the droplet to the cooler surface of the droplet. And that goes into here, BT gets larger, evaporation rate gets larger. Okay. Just a quick to describe what I'm talking about. Initially, liquid temperature of the droplets in the spray as formed above the boiling temperature. A short while later, we limit the surface down to the boiling temperature, and we get heat transfer from hot inside to cool centre. And then a little bit later, we actually allow the surface, if the energy balance equations demand it, to go subcooled whilst keeping the surface still superheated. And if you think about a multi-component mixture, the boiling point is going to rise anyway as the lighter components leave, so limiting it artificially would be wrong. Okay, just a few movies now, just to illustrate some, thank you very much, some flashing sprays. You can see here, this is a slightly superheated GDI spray, multi-hole, etc. But this spray kind of still looks like we'd expect a subcooled spray to look. All the plumes are distinct, and the penetration is still quite large. If we go to a greater degree of superheat, we see a much reduced penetration of the spray, a collapse of the plumes inwards, and it's important. One aspect of modelling this correctly is to model the enhanced droplet evaporation, which will help enhance the conversion of liquid into vapour. And these images are from our spray rig, continuous flow atmospheric pressure spray rig we have in Oxford. So moving on to multi-component fuels. To model a gasoline properly, we need more than one component, and we use Raoult's law for that, which may be familiar to you. We incorporate these activity coefficients to deal with the non-ideal behaviour of the mixture. Those come from a UNIFAC model, which is readily applicable to multi-component mixtures, and the best thing about that is we only need pure component data. We've had success on that in the past. So that's a really easy add-on to the model that we've done. So the first model for gasoline is, let's treat the gasoline as just isooctane. Okay, pretty standard. And we've realised that we've actually, in many markets, got up 5-10% or more by volume ethanol, and certainly more in the future. So we're going to include ethanol as the second part of the mixture of the model for gasoline. So we can use a couple of different models here to model the vapour pressure for the gasoline. If we ignore the non-ideality of the mixture, for E10, say, by volume, we predict about 12 kPa, whereas in actual fact, it's more like 24. So incorporating the UNIFAC model, or some model, is particularly important. So multi-component models. Obviously, gasoline isn't just isooctane, so we've come up with a number of multi-component alkane and aromatic blends that mimic certain distillation curves. This blue is now the base gasoline curve described by this, and we've added a number of different oxygen derivatives with ethanol and methanol in. The non-ideality of adding those oxygenates reduces the initial boiling temperature, and as we add more, we get a greater plateau. As we go to N or E85, basically, we almost have a single boiling point. And the oxygenate fuels are much more susceptible to flash boiling due to that lower initial temperature. Right, so if we've got a multi-component droplet evaporating in our cylinder, there's 3 modes of mixing of internal composition of evolution within the droplet. The first model could be described as well mixed, that is, the evaporation rate is slow compared to the mixing rate. So this might be applicable if the evaporation rate is particularly slow, for example, very early injection, cold fuel, cold air. And in that case, mixing can be allowed to happen faster than evaporation, and the surface composition essentially distills off. So we model it as a distillation curve. That's one limiting case. The other limiting case is the opposite end of things, unmixed evaporation or frozen composition. So this is easy. We just average up the properties and treat it as a single component, unchanging throughout the spray lifetime. And this might be applicable if the evaporation is much, much faster than any liquid mixing time. For example, very late injection, or generally hot conditions. Now, in between those two limiting cases, we have to actually model what's going on, sadly, which would involve modelling this diffusion equation for all but one of the species present in the gasoline. So if we've got a binary component, we only have to do it once. So that's great. And so that is an added layer of complexity. But this should be accurate at all conditions and may be needed at certain conditions. Okay, so let's move on to some results. First we looked at that isooctane ethanol mixture. 10 and 40% by mole, so the binary component is all by mole, remember, and we've got a sort of reasonably cool, very cool ambient conditions. So if we plot the diameter squared history against time for the isooctane and ethanol mixtures, for all of the mixtures studied, and certainly the two here, the well-mixed model, that's a distillation-like approach that you might find in your CFD code, is faster than the unmixed model at this given condition. And we've got a roughly linear decrease of diameter squared, which would be expected from a classical theory. This can be attributed to the fact that in this case, in the well-mixed model, we can lose the ethanol from the droplets early because in this case it's the most volatile species. Once we've lost the ethanol, suddenly our mixture latent heat is much lower, the droplet is unable to heat up a little, and we get a greater steady state temperature of the droplet, and it's the droplet surface temperature that really determines the evaporation rate for these low pressure droplets and sprays. Okay, so a modest difference. We can check the validity of this so-called well-mixed model by, at the cases we think it might be applicable, solving the diffusion equation or the diffusion-controlled effective diffusivity model. And we can get diffusion coefficients from the literature for the species, for the mixture of isooctane and ethanol. And what we ought to do for the non-ideal mixtures is include this multiplicative non-ideal thermodynamic correction factor, which accounts for the fact that the non-ideal species really don't want to mix very well. So this plot, just briefly, this gamma factor, the thermodynamic correction factor, which we can calculate using a unifact code or similar, it's very low. This is the dotted line, very low at intermediate compositions, and that has the effect of greatly reducing the diffusion coefficient and the mixing ability based on what we might expect were the mixture to be ideal. Well, we're actually usually probably more E10, so the difference isn't that much, but still maybe a factor of 10. describe this slide, we've compared the well-mixed model, which is the crosses, to the diffusion control model for a given, this is just a given arbitrary condition out of the ones we've chosen, and we've tested it with both including the gamma factor as a full variable and just setting it to 1 as we'd expect if the mixture was ideal. If we assume the mixture is ideal, the well-mixed model and the diffusion control model track each other very well, as expected because we're at a low temperature. However, with the reduced liquid diffusivity, the lifetime is about 10% longer. Okay, we might want to know about that if we're trying to model our spray evaporation. I can hopefully explain why. Now, if we look at inside the droplet, and we look at one of the species as mole fraction against radius, we see that for the well-mixed model, this just the well-mixed model on the screen now. The well-mixed model shows a flat concentration throughout the droplet. It's well mixed, and that's just at 3 different times throughout the lifetime, black, red, and green. If we add on the diffusion control model, we get a boundary layer as predicted by the formula, but the surface composition at given times is roughly the same, and it's that determines the evaporation rate. If we reduce the mixing ability by including the correction factor for the non-ideality, we initially develop a boundary layer in composition, but then that rapidly stagnates due to the reduction in mixing ability, and the surface composition doesn't really change much throughout the droplet lifetime. So the ethanol stays in the droplet stays at a reduced temperature, and it evaporates more slowly. So we thought then, well, when does this discrepancy between the two models, when is it most apparent, and when might want to consider including it or investigating further? And we found that it's most apparent at very high ethanol contents and also hotter conditions, say higher air temperature or higher initial liquid temperature. That's summarised in this table here. So if we go to really high inlet temperatures and liquid temperatures, then the evaporation rate is faster, and essentially the two different models diverge more quickly, so we get a bigger discrepancy in total lifetime. Okay, I'll finish up by looking at some of the multi-component gasoline model fuel results. First, some subcooled results. So we looked at applying the model gasoline and its E20 and M15 derivatives at a kind of, this is our cold start, very early injection, cold engine conditions relating to some of our tests that we've done. And if I get the plot up, here we can see at this given condition, the limiting cases of unmixed and well mixed in dashed and solid. And here, the unmixed model is the quickest at this given condition. So that's just given by averaging the properties of the gasoline and assuming it doesn't distill as it evaporates. And that is despite the lower temperature we see for the steady state unmixed droplets. We're actually, in the well-mixed case, we lose all those light components and the volatility and evaporation rate greatly reduce. And we see typically that adding methanol in small amounts tends to slow down the evaporation, but adding ethanol tends to speed it up to 15-20%, slightly. So some superheated results, same conditions as before. We've now looked at all of the different, well, up to E85 and M56, which are equivalent stoichiometries for gasoline. Just increased the droplet temperature now so that all of the liquid temperature, so all of the fuels are superheated. And we find that the droplet history may be parameterized for this gasoline model with a linear decrease in droplet diameter to the power 1.5. Now, for a given other gasoline, we might want to tune that exponent based on how it actually distills off. This is for the well mixed model, sorry. And what we see with the comparison between superheated and subcooled, in the superheated we just lose a proportion of mass, maybe 20% of the D to the 1.5 here, in essentially 0 time at all. That's the flashing behaviour of the droplets, and then we get this linear decrease with roughly the same slope, but not quite for all of the fuels. So it might be a way to parameterise the droplet evaporation for multi-component fuels rather than dealing with all of these different components in our gasoline. Adding more oxygenates tends to slow down the lifetime at this low temperature pressure condition. And we've not modelled any flash boiling here based on micro explosions or vapour coming out of the nozzle or anything. This is just a droplet study. Okay, to conclude, one of 2 pages. We've introduced our detailed multi-component droplet model and commented that droplet models for gasoline in general should be able to properly deal with superheated droplets, particularly if you're doing rig tests at or near ambient. Any sensible temperature is going to cause quite a lot of superheat in your droplets, even if it doesn't look like a collapsing spray. We've incorporated the non-ideal vapor-liquid equilibrium, as I've shown is necessary. Discussed the different models to predict multi-component behaviour. We've looked at a simplified 2-component model for gasoline, isooctane and ethanol, and we see that well mixed at a given condition, the well mixed model is faster than the unmixed model, and that at some conditions, particularly faster evaporation conditions, we might want to consider the discrepancy between the non-ideal liquid diffusion model and the well mixed model. And for the multi-component model, we see the opposite scenario to the 2-component model, so that's worth some thought. And I've hinted at some kind of parameterization here to ease our demand on our CPUs for our spray modelling. Okay. Well, thank you very much.